Okay guys, another video here. This one is on electronic spectroscopy. As we've mentioned in the first spectroscopy lecture, UV vis radiation is resonant with the electronic transitions involving valence electrons. And so this is a very useful spectroscopy for studying the electrons that are involved in chemical bonds and the ones that would be involved in chemical reactions. So UV vis is a very important type of spectroscopy. I'm going to show you two examples spectra. One is of molecular iodine in the vapor phase, which is also one of the PChem labs that we're doing this semester. And in that high resolution spectrum, you can see simultaneous vibrational and electronic transitions occurring. In very high resolution spectra, you can also see different rotational states as well. So you can get quite a lot of information out of a UV vis spectrum for small molecule at least. More typically, chemists are interested in larger molecules and they prepare their samples in the condensed phase in a solution of some sort. And there, essentially all of the rotational details are obscured. You can still sometimes see vibrational patterns, and we'll look at a few examples of that. But you lose information in the condensed phase due to broadening of the spectrum. And we've already discussed some of these broadening mechanisms in a previous lecture. So here are the two examples. The spectrum up above, where you see all of these little peaks here. These are due to the vibrations of molecular iodine, and this is one electronic absorption band. So it's a broad band, and then all of the structure that you see here is associated with the vibrational progressions. And there's three. I believe there are three overlapping vibrational progressions in this spectrum, and we'll go over this in the lab portion of the course. The example below, this would be a solution of chlorophyll. I'm not sure what the solvent is, but you can see that there's not nearly the same amount of detail in this spectrum. The peaks are broader. They're more or less featureless, although there are a number of peaks. Perhaps this is a vibrational feature here. Maybe this one as well. I'm not exactly sure. But you get the idea. When you go to the condensed phase, you lose resolution due to broadening. This is a helpful table, I think. It shows different wavelengths of light, their colors. Tells you what their wavelengths are, what their frequencies are, what the energy is, and this is just a handy thing to refer to. And you might even want to go look in the resources section to see what other values are listed in this table. Okay, now this topic is challenging to say the least. I've tried to record several videos explaining the details of molecular term symbols, and it's impossible. So I am going to skip the details and just give you the main points. So for our if you're doing that high resolution spectroscopy on small molecules like a diatom, the diatom electronic states are described by molecular term symbols, and these are analogous to the atomic term symbols that we looked at previously when we studied the electronic structure of atoms. There are some differences, however. Diatomic molecules do not have spherical symmetry. They have cylindrical symmetry. So the cylinder along the bond axis is the type of symmetry that we have here. And angular momentum, of course, is the key idea in describing the term symbols of atoms. And we also have angular momentum of electrons, both their spin angular momenta and the orbital angular momenta for the diatom. The spin part is the same as what we had for for atoms. You have a quantum number capital S representing the total spin angular momentum. You have a quantum number m sub s representing the z component of the total spin angular momentum. And this leads to that lingo where we talked about singlet states and triplet states and doublets, etc. Okay, so all that part is the same. The main difference has to do with the orbital angular momentum. And so it turns out that the total orbital angular momentum is not does not lead to a valid quantum number in diatoms like it did for atoms. Nevertheless, the z component of the total angular momentum vector is a valid quantum number, but it's a little bit different. In a diatom, the z-axis is the bond axis, and so when I'm talking about the orbital angular momentum, or the z component of the orbital angular momentum, I'm talking about the angular momentum of the electrons moving around the bond axis, so kind of revolving around this cylinder. M sub j is the quantum number representing the z component of the total angular momentum. The total angular momentum has a contribution from both the spin and the orbital angular momentum. And so the z component of the total angular momentum vector is also a valid quantum number for diatoms. So the next few slides go through the details, and it is very difficult to explain this without an audience. I need that instantaneous feedback in order to change how I'm saying something in order for this stuff to make sense at all. So I'm going to skip the details, and I'll show you. This is the form for a diatomic term symbol. Okay, there's a symbol lambda in the middle, and it'll be a sigma, pi, delta type of symbol. This refers to the z component of the orbital angular momentum. So that's what the symbol in the middle means. This part here, the spin multiplicity in the upper left-hand corner, that's familiar to us from the atomic term symbols. And so when 2s plus 1 equals 1, we call it a singlet state. When 2s plus 1 equals 3, we call it a triplet state. If you have a single electron by itself, and a single unpaired electron, you'd wind up with a doublet state. 2s plus 1 would equal 2, etc. Okay, so that's the spin multiplicity. The omega is another parameter. This quantum number here represents the z component of the total angular momentum. So it's related to that quantum number m sub j. So you have those three main symbols here. If you have a centrosymmetric molecule, that is one that has a inversion center, then you can also apply this grada ungrada parity label. That's why it's in parentheses. So that isn't always present, but it is present for molecules that have an inversion center. Likewise, the plus and minus is an optional part of the term symbol that is only used when you have lambda equal to a sigma type term. Okay, so for certain types of molecules, you will have the plus and minus and the G and U, but not all of them. It just depends on the state and the molecule that you're talking about. Although we're not really going to use, I'm not going to have you do any term symbols in the assessments, but just for your reference, when you're looking at the molecular electron configuration, that's the stuff that we've already done before for diatoms, right? We had put electrons into sigma orbitals and pi orbitals. When you have a completely filled molecular orbital, in this case, a sigma orbital can take on 2 electrons. The degenerate pair of pi orbitals, say for example the pi x and the pi y orbitals, they can hold up to 4 electrons. When those are completely filled, those electrons make no contribution to the spin multiplicity or to the orbital angular momentum. The consequence of that is that you only really need to consider partially filled molecular orbitals to determine the term symbol of your molecule. These graphics just illustrate various facets of the term symbol, so I'm going to skip over them. And then these problems here, they basically, you work through and try to deduce the term symbols for simple molecules, simple diatoms, using the molecular electronic configuration. Okay, and so we'll skip over these details. It's fun, but it's not that critical for us. For diatoms, the symmetry of these states that's encapsulated into the term symbol is used as the basis of the selection rules. So you can determine which types of allowed transitions you can have for a diatom based on changes in these various quantum numbers that I've kind of glossed over. So as long as you get that idea, then that's sufficient. As far as the details, it's not something that we need to worry about too much. And so we'll go ahead and skip through these. Okay, here's a more important topic, I think, for us to consider. That is how does the vibrational fine structure work in a simple molecule's electronic spectrum? So as I mentioned previously, vibrational transitions will accompany the electronic transition. And for every electronic state that you have, each electronic state has its own manifold of vibrational energy levels. So the ground electronic state of a molecule has a set of vibrational energy levels, and all of the excited electronic states have vibrational energy levels. And what can occur when you have an electronic transition, the electronic transition will also involve changes in the vibrational quantum number of the system. So we'll consider a very simple electronic system, that two-state model. So S0 here represents the ground electronic state, and S1 represents the first excited state. When you have an absorption, so the excitation promotes molecules from the ground electronic state to the excited electronic state, one thing to keep in mind is that because the vibrational energy level spacing is quite large, it's larger than the thermal energy, your initial state in a transition almost always starts from the ground vibrational state of the ground electronic state. Okay, so that's what this notation here means. This double primed upsilon refers to the vibrational quantum number of the ground electronic state, and then a single prime upsilon represents the vibrational quantum number of an excited electronic state. So you can think of the transitions that you're going to see in the UV-Vis absorption spectrum as being a difference of two terms. Okay, this term is for the excited electronic state and its vibrational state, minus the term for the ground state, which in this case is confined to the ground vibrational state as well. This new electronic, that's the wave number difference between the ground electronic state and the first excited state, S1. Okay, so there's an electronic energy term and a vibrational energy term for the excited state. For the ground state, we only need to consider the vibrational term. We assume that the electronic term is zero. We'll take that as our absolute ground state. And if you substitute in the harmonic oscillator model for the vibrational terms, you get an expression like this, where nu prime and nu double prime are the vibrational frequencies on the first excited state and the ground electronic state. Upsilon prime, that is the quantum number for the vibration vibrational state on the excited electronic state. So your observed frequencies, you're going to see a progression corresponding to different vibrational states on the excited electronic state. And so you'll see, as long as there's not too much anharmonicity in the system, you're going to see a set of equally spaced peaks in the electronic absorption band. Let me go to, just want to show you what it'll look like. Well, I had to go really far here. Did I miss a graphic? Don't think I did. Oh, I bet it's in the next section. Okay, we'll look for it later. The intensities of the different vibrational transitions are governed by something called the Frank-Condon principle. And it's based upon the idea that electronic transitions are much faster than how the nuclei move. So the nuclei respond very slowly to the electronic transition. And we call it a vertical transition, which means that when the electronic takes place, it's as if the nuclei don't move, or rather, they retain their same wave function, if you want to discuss it quantum mechanically. So the intensity of the peak is determined by the transition dipole moment, and there's two factors at work here. I've skipped over the math, but one is the transition dipole moment for the electronic wave functions. So the ground electronic state and the excited electronic state, it has a transition dipole moment. And then this term here, this S, represents an overlap between two vibrational wave functions. One on the ground electronic state and the other one on the excited electronic state. And that's going to be illustrated in some of the upcoming figures. But the thing to remember from this slide is that the intensity of a vibrational transition in an electronic absorption spectrum is governed by this Frank-Condon overlap, an overlap of two vibrational wave functions. And we'll see some figures to illustrate that. This slide is meant to illustrate the notion of a vertical transition. Okay, so we have two potential energy curves. This is the ground state potential energy curve, and this is the excited state potential energy curve. It's the potential energy of the molecule as a function of the internuclear separation. So right here we have the equilibrium bond length for the ground electronic state, and right here would be the equilibrium bond length for the excited electronic state. Now when the molecule undergoes an electronic transition, the electronic transition occurs very quickly, and the nuclei don't have time to respond during the electronic transition. However, after the transition has occurred, the nuclei will start to feel a force. So in the ground state, this is the equilibrium geometry, so there's no force acting on the atoms. It's basically sitting at its equilibrium position. But when you undergo an electronic transition, you find yourself in a nuclear geometry that is not the equilibrium geometry. And so as a consequence of that, the atoms are going to feel a force, and it's going to start vibrating. Here's another picture illustrating that. What I'm pointing out, I think another thing to point out in this slide is that sometimes it just depends on the molecule and the states, the electronic states. Sometimes the equilibrium geometries are very close to one another. So there's not that big of a distortion of the molecule as you go from the ground electronic state to the excited electronic state. But in other situations, there can be quite a large difference between the excited state geometry, equilibrium geometry, and the ground state equilibrium geometry. And that will show up in the spectrum. Here, this is the quantum mechanical version of the vertical transition idea. And it also It also illustrates the idea of a Frank-Condon overlap. So your initial state is the electronic ground state, and this wave function here, this is the ground vibrational state of the ground electronic state. So this is your initial vibrational wave function. Okay? And what we're looking at here in the excited state, this is the ground vibrational state for the excited electronic state, and this is the first excited vibrational state for the excited electronic state. Or no, this would be like the third one, I think. I'm trying to count the nodes and determine what the state is. But in any case, what happens is you can imagine when the molecule undergoes a vertical transition, so a change in the electronic state, the vibrational wave function is maintained. So you simply pick up this vibrational wave function and plop it onto the excited electronic state. Now, this wave function is not an eigenstate of the excited electronic state in general. So this isn't one of the wave functions for the excited electronic state. It's something different. In fact, it'll be a superposition of vibrational wave functions up here. And so what will happen is when you drop this wave function onto the excited state, it's going to start sloshing around. Okay, and the Frank-Condon principle states that the intensity of various vibronic transitions is related to the overlap between this vibrational wave function and the vibrational wave functions up here. And so they're illustrating in these little boxes that for certain combinations of vibrational wave functions, you get a good overlap, which means that transition would be strong in the spectrum. But for other pairs of wave functions, you have poor overlap, which would give you a diminished intensity in the UV vis spectrum. So the short thing to remember is that the Frank-Condon principle accounts for the intensity pattern of the vibrational fine structure in UV vis spectra, and the magnitude of the intensity of a particular vibrational transition is dependent upon the overlap of the vibrational wave functions involved. In this problem, they're asking you to explicitly calculate that Frank-Condon overlap factor for different wave functions. It's quite a detailed calculation, and it's more of a project than an example problem, so I'm going to skip the details. But this is the result. Okay, when you've got the wave functions on top of one another, they have a large overlap, and then as the difference in the equilibrium geometry gets larger, you get a smaller and smaller overlap. So they're basically comparing the overlap that you would get when the equilibrium geometries are the same for the two electronic states, and then as a function of this equilibrium position moving away from this equilibrium position. And what you get is what you'd expect, that the overlap decreases as the difference in geometry gets larger, at least for the two ground vibrational states. Well, if you have a ultra high resolution UV vis spectrum, you can also see the rotational transitions, and so the details of that are illustrated here, as before in the vibrational in the row vibrational spectra that we looked at in a previous section. You get these P, Q, and R branches. Okay. I don't think we really need to worry about the details of this. It's not something that I would include as a problem, just because you don't encounter ultra high resolution UV vis spectra very often. But there are some interesting facets to it. But I don't think it's worth our time at this point. much more useful would be some of the content on these coming slides here, where we're talking about more interesting molecules, larger molecules. There, you don't have as detailed spectral information. That is, you don't see all of these different rotational and vibrational transitions, but sometimes you see the vibrational transitions. But you do see you do see characteristics in UV vis spectrum associated with particular chromophores. So, for example, carbon-carbon bonds involve a pi to pi star transition in the electronic states, and they typically occur in a given energy range or at a particular wavelength, at least for an unconjugated system. For the particle in a box lab that we've done, you've looked at conjugated molecules, and there what you find is that the wavelength of absorption for that pi to pi star transition is in the visible range. Just like in vibrational spectroscopy, carbonyl bonds have characteristic UV vis absorption, and there are two transitions that are kind of relevant. One involves a transition between a non-bonding lone pair on oxygen to a pi star transition that is delocalized across this functional unit. It occurs at 4.3 electron volts, roughly 290 nanometers, and those are often somewhat weak transitions because they're symmetry forbidden. Nevertheless, you can still see them because those symmetry rules can be broken or bent, at least. The dominant transition for carbonyl is a pi-pi star type transition. Usually has a very strong absorption because it is a symmetry allowed type of transition. And so you can use these types of transitions as markers for analytical chemistry studies. Here's a table of essentially what I just said. This is illustrating the types of transitions you see. So a pi-pi star transition means that your ground electronic state involves some pi bonding molecular orbital, and then the excited electronic state will involve a pi star transition. So you're promoting an electron from a bonding orbital to an anti-bonding orbital to get to the excited electronic state. Here is an example of the N to pi star transition in the carbonyl. So you've got carbon, oxygen, and then whatever the carbon is attached to. The N part of the transition is a lone pair electron, so a p orbital electron on the oxygen, and then it's promoted to a pi star anti-bonding orbital that's delocalized across the functional group. Here they've given us a compound that contains a carbon-carbon double bond, and it looks like it's got a carbonyl in it. And then they list some of the transitions that you see in the UV spectrum. We see a strong absorption at 213 nanometers, and then a weaker absorption at 330 nanometers. What would those transitions likely be? Well, the strong absorption is going to be a pi to pi star transition, and that would probably correspond to the carbonyl, I would expect, because the carbon-carbon one would be a bit lower in wavelength, perhaps, or well, it may be that the whole group. Now that I think about it, there could be some delocalization here, and so this may very well be the pi to pi star transition for the entire chromophore. The weak one would certainly be the N to pi star transition involving the lone pair on the carbonyl oxygen atom. Transition metal complexes, they involve d orbitals, And when you have different ligands attached to the transition metal, what happens is the d orbitals get split into different groups, just depending on the ligands that you have and how much coupling there is to the d orbitals. And so you can have transitions between the different d orbitals, which are interesting. And then you can also have electronic transitions where charge is transferred from the ligand to the metal, or where you have charge transfer from the metal to the ligand. So you have these different charge transfers that can take place. You can also have transitions amongst the d orbitals. These lead to some interesting states. Particularly the charge transfer states are important because they can have relatively long lifetimes, and then they have technological applications as well in terms of photovoltaic materials, solar cells, that type of thing. This is a figure illustrating the splitting of the d orbitals in this titanium complex. The magnitude of the splitting, this delta 0 here, depends on what ligands you have attached to the metal. This is showing us the classification of the different levels after they've been split. And this has to do with group theory, and where the ligands are relative to the orbitals determines which ones go down in energy and which ones go up in energy, essentially. Here is a spectrum of this titanium complex. That we have a large peak near 24,000 reciprocal centimeters, corresponding to an energy difference of 3 electron volts. It involves a transition between these T2G orbitals and the EG orbitals. And that from the spectrum you can determine what that splitting is. So the UV spectrum tells you something about how strongly the ligands are coupled to the metal. Well, we'll stop this video here.